Welcome to the second video lecture in week 4 of the discrete mathematics course. In this video lecture, we will continue with our understanding of induction. Now, to quick recap, we were looking at the proof techniques, namely to prove how to prove A implies B, and we have seen that there are quite a number of different proof techniques available to us. Constructive proof, proof by contradiction, contrapositive, induction, counterexample, and existential proof. Now, this is a slide I have shown you every time, which basically says that there is no rule of which proof technique should be applied to which problem. It's a art that you have to develop. Now, to quickly recap of whatever things we have done till now, we saw some tricks of how to split the problem into smaller problems, depending on whether the B can be written as C and D, how to remove redundant assumptions, and thirdly, how to see that sometimes proving something harder or stronger can be easier. We also saw some proof techniques, namely we looked at the direct proof technique where one just works with A and then end up proving B, or one can go backward, meaning you can start simplifying B and slowly get to a situation where A implies C can be easier to prove, where C is equivalent of B, just a simplified form. So we saw some few examples of this. We also looked at the case study. So in this case, if we split the assumptions into some constant number of cases, so what happens is that if you write A as C or D, then A implies B gets split up as C implies B and D implies B. This particular case study proof is something relevant to the proof by induction also. We will see it very soon. So other than the case study proofs, we also looked at the proof by contradiction, namely proving A implies B is same as proving not B and A is false. Or in a similar way, one can prove A implies B by proving that not B implies not A. This second one is known as the proof by contrapositiveness, and this can be useful particularly when B can be written as C or D. In that case, A implies B can be written as not C and not D implies not A. We also saw this case of proof by counterexample, where if we have given a problem of this form for x, for all x, prove that proof or disprove Ax implies B. To disprove this statement, one needs to give an x such that Ax doesn't imply Bx. Or in other words, we have to give an x such that Bx is not true, but Ax is true. Right? So these are the proof technique that we saw last week. In the last video lecture, we started with this proof by induction. Now, the proof of induction is very similar to the case studies proof, except that in case studies, one splits the assumption into a constantly many number of cases, and thus the problem gets split up into a constantly many and of some small problems. But there are times when one can split up the assumptions into infinitely many but countably many number of cases. So in that case, of course, just in the case of case studies, the problem gets split up into an and of a infinitely many number of problems. The sub-problems are usually we look at parameterized by some parameter of the input or integrated by some parameter of the input. So in other words, one writes this whole thing of A implies B as P1 and P2 and so on, and it's an infinite collection of them. So thus, to prove A implies B, one needs to prove that this Pi holds for all the i's. So we saw some few examples of how to split up the problem. So the example that we saw last time was that for all n, if we have to prove that for all n, if we have to prove that the sum of first n integers is n into n plus 1 by 2, we can then split up this problem as for a particular k, the sum of k integers, first k integers is k into k plus 1 by 2, and then we have to prove that this statement is true for all k. So this problem becomes, we have to prove is basically AND of all the pi's, where I ranges over all the possible integers, natural numbers. Similarly, if the problem is for all n greater than or equal to 1, prove that 11 divides 23 power n minus 1, we can split up by, again, we can induct on n, which means that we can say that, okay, pkb 11 divides 23 power k minus, so it should be minus 1, 23 power k minus 1, and we have to prove that this statement is true for all the pk's. The third example is the A and Bm inequality, namely the average of or arithmetic mean of any n positive real numbers is more than or equal to the nth root of the product of these n real numbers. And again, here we induct on n, and thus we define pk as take any k positive real numbers, then prove that statement for those k real numbers, and then pn, or then the actual problem says that for all k greater than or equal to 1, prove that pk is true. Now, these are all examples of how a problem can be split up into an infinite number of subproblems. But once we have this infinite number of subproblems, how do we solve them? To prove this infinite number of subproblems, surely we cannot go on solving every one of them because they are infinitely many. So one way of getting around it is first prove the first one is true, first prove that P1 is true, then prove that for any k, if pk is true, then pk plus 1 is true. If you can solve that, we expect that. So the idea is that if you look at this whole real line, then I have first proved that P1 is true, and this statement says that if P1 is true, then P2 is true. Now if P2 is true, then P3 is true, and so on. So I can keep on basically filling up the whole real line, meaning for all k between 1 to infinity, I would be able to prove that this statement is true. So by doing so, that means first proving P1 is true, and then by proving pk is true implies pk plus 1 is true, we would be able to prove that for all n greater than or equal to 1, the problem Pn is true. And hence we will be done. Now for this one, what we need is a particular axiom which states that whatever we are doing is correct. And this is what it says. It is called the principle of mathematical induction. And it says that for any predicate, if we first prove P1 is true, and for all k greater than 1, if I can prove pk is true implies pk plus 1 is true, then that means that for all k, we end up proving pk is true. It's a roundabout way of proving that for all k, pk is true. It's a very powerful technique that we will be seeing more of it in the next couple of weeks. Now, so to prove this statement using the mathematical induction, there are three basic steps. The first step is what we call as base case, which basically means that P1 is true. Note that all the three cases is true is important. Namely, if I don't start with the base case, then there is no way of starting this whole process. So the base case is required. We have to first prove that P1 is true. Second case is that we have to assume, this is called the induction hypothesis, assume that pk is true for some k greater than or equal to 1. And say that okay, if pk is true, then using inductive hypothesis, prove that pk plus 1 is true. Now these three steps, if you can solve them, then we prove that the whole problem is true. All the three steps are essential. So the steps are basically P1 is true, then defining the induction hypothesis, and then using induction hypothesis prove the next one is true, thus the inductive step. So in the last class we saw one particular example of how to use induction, mathematical induction for proving the sum of first n integers is n into n plus 1 by 2. In this video, let us look at a second one. Now to prove this statement, this problem of 11 divides 23 n minus 1, of course we have to follow the three basic steps, namely give a base case, induction hypothesis and inductive step. So in other words, this is the problem. The pk says that 11 divides 23k minus 1, and we have to do the base case, namely P1 is true, inductive hypothesis, namely let's assume for some k, pk is true, and inductive step, assuming pk is true, prove that pk plus 1 is true. Now putting the values of pk or statements of pk and pk plus 1 in this setup, the thing that we have to prove is that the base case becomes 11 divides 23 power 1 minus 1. The inductive hypothesis says that for some k, 11 divides 23k minus 1, and assuming that 11 divides 23k minus 1, prove that 11 divides 23 power k plus 1 minus 1. And now let's see how to prove them. First of all, the base case, 11 divides 23 power 1 minus 1. Now this is obvious because 23 power 1 minus 1 is 22, which is 11 times 2. Now the inductive hypothesis states that 11 divides 23k minus 1. Now assuming this 11 divides 23k minus 1, we have to prove that 11 divides 23k plus 1 minus 1. Now let's see how to solve that. So 23 power k plus 1 minus 1 is nothing but 23 times 23 power k minus 1. If I write 23 as 22 plus 1, we get this number, which is 22 times 23 power k plus 23 power k minus 1. Now by induction hypothesis, 11 divides this 23k minus 1. And the first term, which is the 22 times 23 power k, is divisible by 11 because 11 divides 22. So thus 11 divides both this term, and thus 11 divides the sum of these terms, which is 23 power 2k plus 1 minus 1. So thus, as you can see that the inductive step is not a hard thing to prove. One can easily get the inductive step if we follow it correctly. We have to apply the usual techniques of direct proof or proof by contradiction. But this inductive state, the base case and the induction hypothesis, along with the, of course, the principle of mathematical induction, helps us to prove that this statement is true for all k, or in other words, for all k 11 divided 23k minus 1. Thus, we have proved that for all n, 11 divides 23n minus 1. Again, I ask you guys to prove this statement or try to prove this statement without using induction. Now, proving some statement like this without using induction can be quite a tricky job. I finished this video today leaving two exercises. The first one is prove that the sum of 1 plus 3 plus 5 till 2 n minus 1 is n squared for all n. In other words, the sum of first n odd numbers is n squared. And second one is that if x is greater than minus 1, prove that for all n, 1 plus x power n is greater than 1 plus nx. So these are the two exercises which can be solved using the induction technique that we have seen so far. In the next video, we will see interesting versions of this induction hypothesis which will help us to solve in more interesting problems.